Jnanam paramam dheyam. Knowledge is supreme.
Now that the parameters of absorption and emission are well defined, let us go over and try to understand how the actual measurements are made. To do that, let us first draw the schematic of an absorption spectrophotometer. And the kind of spectrophotometer we are going to describe here is called a split beam spectrophotometer. Okay. What do we have? I am drawing the schematics first, then we will go into a little bit of a detail of some components of the spectrophotometer. First of all, of course, you need a light source, which is usually called a lamp. What is the light source that you use? Depends on what kind of energy regime that you want to probe. Okay. Usually, you want a light source that gives you a wide range of wavelengths, as we had discussed the previous day. So, you want a source that gives you what we generally call white light. White light means light that contains all possible wavelengths, preferably in the same ratio. It should be uniform across the spectrum. Then we have something called a monochromator. The box is too small to write chromator. What is there inside a monochromator? What do you have inside a monochromator? White light. I want to get specific wavelengths from there. What should I use? A grating, right? But not just grating, we will come to that in a while. So, that gives you the color that you want, let us say color of wavelength lambda. Now, if you are doing absorption spectrophotometry, remember we need IT as well as I0, isn't it? What do you want to measure? Absorbance. Absorbance is log I0 by IT. So, one way of doing it, there are 2-3 ways of doing it actually. One way of doing it is to insert a beam splitter. A beam splitter, as the name suggests, is an optical component that splits the beam into two parts, meaning it transmits a part of it and reflects a part of it. Now, we are talking about something that reflects. So, you can think of it as a partially reflecting mirror. Okay. In fact, if you take a glass slide itself can act as a beam splitter. If you make laser light, especially wavelength on a glass slide, you will see most of it has gone through, part of it gets reflected. For glass slide, that typical number is 4%. 4% gets reflected, 2% from the front surface, 2% from the back surface. Remaining 96% goes through. In absorption spectrophotometers, generally what you use is a 50-50 beam splitter. 50-50 means half of the intensity of the light goes through, half gets reflected. Okay. Then you have this mirror which produces a parallel arm of the light. Here, when in one of the arms you put in your sample, in the other arm you put in your reference, and then you put in a photodetector, I will just write D for it, which can measure the intensity of the light that reaches it. Now, from this detector, what is the information we get? I0 or IT? Louder, IT, right, because this beam passes through the sample. So, from here we get IT, and from here obviously we get I0, right. Generally you want to put in everything except your sample in the in the reference side. Suppose you are working with a solution, then you want to put the solvent inside an identical cuvette on the reference side. Now, in case there is any absorbance by the solution, it gets corrected for. Okay. So, from here you get IT, from here you get I0, and then the computer processes the data and gives you an output of absorbance right away. Okay. This is how this is a schematic of an absorption spectrophotometer. What about emission spectrophotometer? Just a sec. Now, for emission you see what is the difference between absorption and emission? Absorption means you have two energy levels in the molecule, something say 1 and 2. You shine light of appropriate frequency which matches the energy gap, Bohr resonance condition delta E equal to h nu, and there is a transition from 1 to 2. This is the process you are following when you do absorption spectroscopy. In emission what happens? You need a particular frequency, I will call it nu Ex, to perform this excitation, and then usually something happens in the excited state. More often than not, the emissive state is not the same as the excited state. Okay? So, let us say emission takes place from here, and let us say this frequency is nu Em. If you are more comfortable with lambda, you can use lambda wavelength. Okay. So, now see, it is not enough for me to choose one frequency, I have to choose two, one for excitation and one for emission. I have to excite the molecule by the proper frequency, and I have to record the intensity of the emitted light at the frequency where it emits. When you look at emission, any emission event has to be preceded by excitation, right? And for excitation, any wavelength is not good enough, any energy is not good enough. You have to supply light of frequency such that delta E equal to h nu, that condition is fulfilled. If this is delta E and let us say this is nu Ex, h nu x must be equal to E2 minus E1. Okay. So, there how will I get that nu Ex? By using some monochromator. So, I need a monochromator to select the excitation light. Clear about that? So, let us actually start from there. I have a lamp, then I put in a monochromator. I will call this excitation monochromator. This chooses the frequency or wavelength, whatever you want to say. This chooses nu Ex. What determines the choice of nu Ex? The energy gap between the state, the ground state and the excited state to which I am exciting. Okay. Now, this light goes and is incident on the sample, and sample let us say emits. Now, usually the light that is emitted has lower energy than light that is used for excitation. In special cases, it can have higher frequency, higher energy, that is called upconversion, but that would involve what is called a two photon excitation, multi-photon excitation. But in the simple case, what happens is after you excite, generally before the molecule can emit, it undergoes some kind of relaxation in the excited state. Relaxation causes a decrease in energy. There are different mechanisms of relaxation. I am not sure whether we will have time to discuss that in this course, alright, but it undergoes some relaxation. It is not easy for it to go up, right, unless you provide more energy, but coming down is not very difficult. So, it usually comes down to a lower energy state and emits at a lower frequency, nu Em. I want to now study this emission, okay, nu Em. How do I do it? I have to, and Okay. Usually this emission is not monochromatic, emission is also polychromatic. It is not white, but usually the emission has bands. There are several energy levels that can be involved in emission process. From there I have to choose the frequency that I want to work with. So, let me not use yellow there. This is your emitted light, even that has to go through what I called an emission monochromator. Which allows me to choose the frequency of emission which is then detected. We need 2 monochromators in an emission spectrometer. Are we clear about that? That is why usually emission instruments cost, well, that is one of the reasons why emission instruments cost more than, significantly more than absorption instruments. One, but not the only reason. There are several reasons actually. Okay. So, these are the schematics. Now, one question that we would like to ask is, what is there inside a monochromator? We know there is a grating, but it cannot be just a grating. Let us see what is there in a monochromator. Maybe we can understand this question better then. What do we have inside a monochromator? Of course, we have a grating, right? We have discussed this already. A grating disperses the light and breaks it down into its components of different frequency. How? What is Bragg's law? N lambda equal to 2d sin theta, right? I will only work with n equal to 1. When n equal to 1, you call it first order diffraction. Generally, it is more prominent than second order diffraction, second order is more prominent than third order, so on and so forth. So, I will just write lambda equal to 2d sin theta. So, for different values of lambda, theta will be different, okay. This is basically the principle. But now the problem is this, I have some light source, okay, can be the lamp or can be the sample itself if you are talking about emission, okay. It is always considered to be a point source, okay. Now, if it is a point source, in which direction will light be emitted? All direction, right. Unless it is a laser, we will talk about lasers later on, but there is a reason why lasers are have such a highly directional output, it is not straightforward, okay. If you just take a simple lamp, something like a tube light, then light goes out in all possible directions, okay. And here I have my grating. So, if light falls in many different directions, then we got a problem, isn't it? Because then all colors will be will go in all directions, okay. I must have a parallel beam of light falling on the grating. Is this point made? I cannot have a divergent source and light from a divergent source falling on the grating directly. Is that point made? Have you understood? So, what is one way of doing it? I can put in a lens, I can put it in such a way that this light source is exactly at the focus, that is going to give me a parallel beam, alright. And then what will happen? If lambda 1 is a particular wavelength, lambda 2 is another particular wavelength, goes in this direction, from this part also it will go in parallel direction. Are we clear about that? Because theta has to be same. What about lambda 2 if I select some other wavelength? Let us say it goes in this direction, this will be parallel, okay. But there is a problem with this arrangement. The problem is, if this is the case, then my grating has to be exposed right after the lamp, and in that case ambient light can get in. Understand? If my instrument is absolutely open and if I have just the point source and the grating, then I cannot have anything in between, right? Then light from tube light will always have to will also get in, which means we have to always perform the experiment in a dark room, like we perform this physics optics experiments. but then who wants to stay in a dark room all day? So, one way of avoiding this problem would be, let me draw it again. Let us say this is the situation. This is my grating. One way of stopping external light from getting in, ambient light from getting in, would be to put in a slit. What is the meaning of a slit? This is a slit, right? If I look like this, I can only see her, nobody else, right? All other light sources are blocked. So, I can put in a slit. What is the problem of putting a slit in this kind of an arrangement? Yes? Yeah, big time. Intensity is decreased, means almost no intensity gets through. So, your signal is going to be very, very small. So, one thing is for sure, I have to use a slit. In a monochromator, a grating is not enough, a slit is required. But then if I want to get in more light through a slit, if I want to get all the light in through a slit, then what is the only way in which I can do it? I cannot use a parallel beam falling on the monochromator slit, right? I have to use a focused beam, and the focus should be at the slit. Okay. So, the right arrangement would be not this, but something like this. L for lamp, L for light. The correct arrangement would be use a lens and focus it like this and put your slit here. If I focus tightly, then what will happen? All the light gets in through the slit, right? But what is the problem? What is the problem with a beam that is focused onto the slit? It is going to be divergent from the slit, right? So, now see, this is called the entrance slit. So, now effectively the entrance slit becomes a light source. Okay. This is entrance slit to the monochromator, that itself becomes a light source. And one thing I should say is that generally lenses, well, I will not say lenses are not used, but it is better to use mirrors, curved mirrors rather than lenses, because as we discussed earlier, if light goes through anything, then some loss is there. It is better to just reflect from the surface. Okay. So, now before it can fall on the grating, I have to do something to this light, right? I cannot let a divergent beam fall on the grating. I have to collimate it now. How do you collimate? This is how you collimate. The problem is, wait, let me make a narrower beam. So, something like this. Otherwise, I will have to draw a really big mirror. Let us say put a curved mirror here, and now you put a curved mirror in such a way, this is your entrance slit. Put your curved mirror in such a way that the entrance slit is exactly at the focus of this curved mirror. Now, what do you get? You get a parallel beam of light. Parallel beam of white light which retains all the intensity of the light that has been captured by this lens or by the mirror that I have put behind the lamp. Clear? Now, I put my grating here. What will happen? Let us say this is lambda 1, I will just write 1. I get a parallel beam here. What else? Where is my blue chalk? wavelength number 2, wavelength number 2, another parallel beam. Now I have to get the light out, right? I have got the light in, white light in. I have to get the individual frequencies out as well. For that I will need another slit, and now I think you might understand better. What we do is you have another curved mirror here. So what this curved mirror would do is that it would focus all the yellow beams, yellow rays to one point, and would focus all the blue rays to another point. Is this point clear? Right? We have, the way we have drawn it, we have two parallel beams, one yellow and one blue. Okay. So focus all the yellow rays at one point, focus all the blue rays at another point. Now if I put in another slit, and let us say the slit is like this, what will happen? The yellow rays will get through the slit and blue rays will be blocked. Okay. Now suppose, now I am trying to answer your question. Are we okay so far? Now say, before that, of course, what you do is, all you have to do is you put your detector right here. Generally you want to put your detector right at the exit slit of the monochromator, because that is where all the light energy is focused. Now suppose I do not want the yellow rays, I want the blue ones. What do I have to do? One thing I can do is I can move the slit. Okay. Right now I can see only Vikas. If I move it like this, I can see only Shobna, right? So I can move the slit. But then, as I told you, we put the detector on the slit. So generally you do not want to move the slit and the detector. What else can we do? Exactly. So what you can do is, you can change the tilt of this grating, right? If you change the tilt of this grating, depending on the tilt, you can choose which frequency will come out, right? So what are fixed? The slits are fixed in position, the concave mirrors are fixed in position, the grating is usually something that you can tilt like this, and depending on the tilt angle of the grating, you can get whatever frequency you want to come out of the exit slit. This method is called scanning.